Okay, I have your exams. I've posted the answer key for the exams online, and I'll hand you back yours at the end of class. I haven't put in all the scores yet. I'm going to do that today. So when I release everything, it should give you an approximate, your percentage should be an approximate where you're at. There'll be a little bit of a curve on the exam from 161 to 155, so that's already locked into Canvas. Okay, couple things. So I have copied over and placed in the for today, Wednesday, and Friday on Canvas. I've placed the reading assignments, and I'll put the videos, and I'll put any homework problems, although I suspect the practice problems that I have are already in the old. Some of them are already in the old practice problems, particularly the ones where there were the 4 cyclohexenes and you had to add each of the reagents. We still have 3 more sets of reagents to talk about. And so those ones are there. I'll put some more practice problems. At the end, in the last folder on Canvas, I've placed, let's see, there should be a folder called Review Questions for the Final Exam. So there's about 70 or so practice problems in this folder that you can print out. I haven't released the answer key yet. I will do that probably Wednesday or Friday. So it'll give you more practice problems to work on for the final. Free radical halogenation is in here, which is not on the final, but there's no real naming. The extensive naming that we did, so I'll have to put together some more naming problems from chapters 1 and 2. But everything else should be there. There's probably alkynes there that we'll start with next semester. So there's more practice problems there. In the library, there's an ACS study guide that has multiple choice problems broken down by topic. So they have like addition reactions, they have SN1, SN2, E1, E2, so those will be there as well. And those are on 2-hour reserve in the library.
Wait, so is this final your questions or ACS?
So this final is my questions, but if you want more multiple choice questions, they're in the ACS study guides that are on 2-hour reserve in the library. These ones are multiple choice, the ones that are on Canvas as well. And then you can use TopAd or go back through old exams, etc. if you want practice problems for the final. But the final is my written exam, and it will change a little bit because I have to take all the free radical halogenations and put in some naming questions. So it won't be exactly like it was last year. So the reading assignments for today, Wednesday, and Friday are up already, so that you can take a look at those. The problem sets, or the chapter 12 problems, are due on Sunday at midnight, because we'll be finishing up some of the chapter 12 problems on Friday.
The chapter 12 homework didn't show anything correct.
Okay, if I don't get to it after class, somebody send me an email and I'll correct that button. I just looked at it today. I thought that button was pushed.
For the resume, I was looking at the syllabus.
We'll get to the resume in a minute. It's on my list. We'll get to the resume in a minute. So that's the organic part of stuff. Second issue is course evaluations. You should get an email today, from Canvas saying, inviting you to take the course evaluation. We're using a system. Normally I control that out of Qualtrics to do a survey, but this is coming out of Canvas. So you'll get that sometime today. You have until next week to complete it. I'll talk more about that on Wednesday in terms of how I use it and incentives for you to fill it out, but you should get an email today. All right, the resume. So they had promised me in Career Services that people would be placed into or have access to Canvas websites for the College of Arts and Sciences Professional Development Program, which is what this is. It's a mini version of what Bowler has. And so they haven't done that yet. I think those of you that are juniors or seniors and biology majors, they loaded up bio majors first. Committed or declared bio majors. They created a Canvas website for them, of course, because it's biology. Anything that happens always happens with biology first. Not that I'm annoyed by that, but I am. So some of you actually have access to the Canvas site. Let me just take a minute or two to explain. So College of Arts and Sciences is coming up. Well, basically they're borrowing the Bowler School, professional development. If you don't know what the Bowler program is, basically they have to do things from their freshman year on in terms of developing resumes, interviewing skills, cleaning up social media. There, I think they even have you change your phone greeting so that, like, if a prospective employer calls your cell phone, it's not like, hey, dude, what's going on? It's something more professional than that as a greeting. And then looking through your social media to make sure that it's professional and not unprofessional. But we have a smaller version of that. So each major within the College of Arts and Sciences is supposed to have told Career Services, hey, we want this many workshops that are required, and then so many that are like you choose from different workshops. That's all supposed to be loaded onto a Canvas site that you would get access to. Even before you declared as a major, you would get access to that. Then when you become a major, it lays out what the criteria are. I believe in biology, it's going to be a requirement for to graduate. I can't do that yet in chemistry because I'm not going to not graduate somebody because they didn't write a resume. I got more problems than that. So it'll be, but we're strongly encouraging people to go through this. So what I did at the beginning of the semester was to say, okay, let's put one of those requirements into the class as like a quiz. But they haven't put people into the Canvas sites. So for instance, the resume, they used to have a bunch of workshops on how do you do your resume. Then you would do your resume and then you would have it approved and that is checked. What they've done is they've created it so that when you have an approved resume, you've met that requirement. And on Canvas, there's a online kind of tutorial on how to create your resume that not everybody has access to now because they haven't loaded up undecided people. And most of you are probably still undecided in terms of major because you haven't declared yet. So I just called them today. They said, well, maybe the thing to do is hold off. So if you've already had a resume approved and it's up on Handshake, which I believe is their software, then you're good to go. You'll just want to keep that updated. And so I think everybody's going to get credit for that, for the quiz, for the resume. If you've already got it approved, that's great. They'll send me your name. If you are like planning on doing that this week or you made an appointment with Career Services, keep it and get it done. Next semester I'll put the resume, you'll see it again, as well as probably a LinkedIn profile, and I may have another quiz where you do cover letters. Now the reason I'm doing this, and those of you that are pre-health oriented, are going, why waste my time? I am not wasting your time, because Dr. Lee is also putting together and participating with this. The idea here is to have, for those of you that are sophomores, now is the perfect time to get your resume together and start updating it. Because in the spring, there'll be lots of internships and other opportunities, and the first thing they're going to want is a resume and maybe a cover letter. So that's why I decided this semester would be good, and next semester will be equally good. So that way you can get your resume together so that you have it for that. If you had it done last year, that's great. You just want to keep it updated and in a format that they approve. And they know what the science formats are versus the formats in the other disciplines. Bobby? So next semester I will also put on, I think it'll be 3 quizzes that'll be dedicated to that. And so in that way, people will be on the Canvas site. They can go and do that online. And then once you have like an approved LinkedIn site, then check that that's been completed. You have an approved resume online, check, that'll be taken care of. Cover letter, same way. So then you'll have these resources already done. The biology department will thank me, for those of you that are biology majors, for forcing you to complete those requirements. They won't thank me, but it'll get done anyway. The reason I'm asking for the reason that LinkedIn is one of the ones that chemistry has required is because I have a very difficult time as chair figuring out where people do internships. And I'm sure Dr. Dranowski's in the same position. And so if you have a updated LinkedIn site, then you have something that you can point, people to, but then you can keep track of like where your internships are, and I can do that as well. So it kind of helps me keep track of where majors are interning and where graduates, people say, well, do we have any graduates at BASF, which is a chemical company down on Chagrin Boulevard? And I don't know, I type up BASF, and sure enough, all of our graduates come up, and there was one who's in Detroit. So, but I can find out what we have, where our alumni are. So it'll help us as a university kind of keep track of where you're at. And I get these requests over the summertime. Somebody will say, can you, within 24 hours, tell me where all your chemistry majors are interning this summer? And then I pretty much just shoot myself in the head. Because how do I get that information? Then I send out an email and say, okay, I realize not every one of you is going to respond to this, but here's what they're asking me. And you usually get a pretty decent response back. But that way I can keep track of that. Part of the reason why we had the STEM career fair is because, you guys are all responsive to that, but also that we've had a lot of interns go to those various companies that we're talking about. So that helps everybody, because then it gives you more internship opportunities, as well as, opportunities at the clinic and other places. So what I'm going to do is, if you've got your resume done, that's great. If not, you'll get a Canvas website over break, I think. And then you can go ahead and start working on one and then get it approved maybe early in the semester so you've got it. And then I'll also, I think, be requiring, like I said, LinkedIn. But you'll see that in the syllabus for next semester.
If we can't take next semester, like topics, and can we still do those things?
I'm going to talk to Dr. Kwan and see if it's possible to have him do that as a requirement as well.
All right, if he doesn't do it, we can come to you to get help.
Sure. Yeah, you can do that. I just, and they touted this as, oh, look, because then it's like being efficient because you're doing this for class and also then getting credit for the major. And they were the ones touting this, and then it was more complicated to get everybody in a Canvas site. So it'll come, and so that's the status of the resume. But for those of you that even if you're like, I'm pre-med all the way, Dr. Lee's going to have you do this. And again, it's about professional development regardless. We're not, as a university, we're not necessarily riding the front of the wave in a lot of things, but this is actually something that a lot of schools have looked at and go, oh, you guys are way ahead of us on this. But I know in the Bowler School, it's the Bowler School. I mean, their internships are very highly structured, but we're working towards that, because that's one of the things that our majors asked for a few years ago. Is they said, how come we don't have anything like this? And so the College of Arts and Sciences put it together. So, and in chemistry, 40% of our students go out and get jobs when they graduate. And then a third too. Then it's about a third, but a little bit more, about 40% go on. So it's important. If you're a chemistry major, you have that option. If you're a biology major, you might work as a chemist someday. A lot of biology people are out there working as chemists, not getting paid as chemists because they have biologists, but still working in the chemical industry.
What happens to the other 60%?
Either go to graduate school or pre-health or health professions. But unlike biology, I think it's pre-health than jobs. But ours, people go on to employment. Now they may eventually go back to medical school, dental school, etc. But that first landing afterwards is usually a job in a chemically related thing. It's just a different. It's more options. There's a lot more options for employment for chemists than there probably are for biologists. I think that's a true statement, but there's a lot of biologists that work as chemists. So that's where that stands. So okay, and I went through this all this morning. So if you're thinking I already got everything timed out. All right, so you get the course evaluation email that you can go ahead and fill out at your leisure. We'll talk about it on Wednesday. And then Chapter 12 problems I'll take a look at, but they're going to be due on Sunday. I think your final next week is what, Monday or Wednesday? It's on Wednesday. So if you don't quite get it done on Sunday, but again, getting the problems done, studying for the final, that's all together. And doing the problems is studying for the final. Right? It's not a separate task that is unassociated with the final exam. So, okay. Any other? And I probably anticipated that this would be the week that most people were going to probably take care of the resume thing anyway, but it's kind of late in the process. So, again, if you got it done, great. If you in the plans, go through with it because it'll be helpful. All right, what topics do we have left? We got a couple of reactions. We have 3 reactions left. They're going to go on the chart. So we're going to again be asking our big 3 questions. What am I adding? How Markovnikov, anti-Markovnikov, 50-50, cis or trans. So let's look at mercuration, demercuration. Now, mercuration, demercuration looks an awful lot like a bromonium ion. So let's start with taking a generic double bond, and I'm going to add to this mercury acetate. Now, mercury is a +2 ion, and this OAC is a deprotonated acetic acid. So it's a 2-carbon acid, and it's deprotonated. So we've got a mercury 2+ and 2 negatively charged anions. So this is a 2-step mechanism, and the first step resembles a bromonium ion. And here's how it does that. So if I'm taking my double bond and I have my mercury acetate, so I got my mercury attached to two acetate ions, or having two acetate ions as the counter ions for the mercury 2 plus. I'm going to take this pair of electrons, give it to the mercury, and kick off an acetate. And that's going to basically leave me with an Hg acetate, which overall has a positive 1 charge. Because I've lost one of the negative charges in mercury's 2 plus. So this whole thing is a +1 charge, just like the bromine was a +1 charge in bromonium ions. Now mercury is big enough to fit over both of the carbons, so that in this case, because mercury is an ion itself, all 3 atoms in the triangle are going to share a positive charge. So some of the positive mercury charge is going to end up down into the carbon. So basically, for mercury, we can say it's delta positive, just like the 2 carbons are. Now, bromine doesn't have much of an affinity for a positive charge, so it kind of pushed all that electron dense, or pushed that charge down into the carbon. Okay, so now what I have is a triangular intermediate with, again, mercury acting very much like bromine.
No transition states for these?
No transition states for these ones, just like there weren't for the bromine. So really what I have is I have a mercurium ion, the equivalent of the bromonium ion. And so now all the characteristics of the bromonium ion are in play. Triangular intermediate means what? 100% trans. Square intermediate, cis.
Why is there not a pressure bond between the two C's?
Because what's happened is that double bond is now taken up by these 2 partial bonds.
Okay, I thought that when we did intermediate to the other ones, like when we did the square, there was one there.
There was one there because that was a transition state.
Oh.
This is an intermediate.
Oh, okay.
So this isn't a transition state. This is an actual intermediate. So the double bond's been used to form the 2 partial bonds. Okay. So now I'm going to add water to this. And I should have said at the beginning, mercuration, demercuration is a way to add H and OH to the double bond. It's going to end up Markovnikov, and it's going to end up 100% trans. And you can see why it's 100% trans, because of the triangular mercurium ion. Okay. So now if I'm water, I'm forced to add opposite the mercury. If I go back here and I make this alkene now very specific in terms of adding 2 alkyl groups to the left and 2 hydrogens on the carbon to the right, the mercury is going to have to add underneath. Which carbon is it going to add to? The one on the left or the one on the right?
Wait, the mercury or the water?
The water. How many people say left? Right? So the water in a triangular intermediate like this, the nucleophile always adds to the carbon that is most substituted and has the most delta positive charge. So the mercury is going to add to the carbon on the left. Sorry, water. Water's going to add to the, they both start with H. The water's going to add to one on the left. It's the last week, right?
Yeah.
Yeah, well, don't quit. You still have 2 weeks left before you can quit. Right? This is a time when I tell my Dr. Weaver story about when I first got here now 24 years ago. And he said, well, they just don't listen to you for the last couple weeks. And I go, couple of weeks? It's like, they're everybody's dead. And I having taught at OU where people listened to me or didn't listen to me for much of the 10-week period, I'm like, well, I guess that's an improvement. But don't do that. You can quit after your last final. If you quit before that, you're going to have a lot of regret. So, all right. So the water's going to add to the carbon on the left, and then the mercury is going to slide over, just like the bromonium ion. And so that's going to make, then we're going to have an oxonium ion, just to make sure that we're exactly complete on this. We're going to have an oxonium ion then that added trans to the mercury and added to the most substituted carbon. And then we break the bond and we lose the H plus, so that our final product then, again, has added OH and the mercury trans. And if we treat the mercury acetate plus as being H plus, or being equivalent to H plus, the mercury has added Markovnikov. Because the mercury plus has added to the carbon with the most hydrogens. So again, this is exactly like a bromonium ion. If you go back and you replace the mercury with a Br, you'll see that we did this before. So this sets the regiochemistry, the Regio Selectivity, as being Markovnikov. It also sets the stereochemistry of being 100% trans. But you said you added H and OH. We've added an OH and a mercury. Where's the H come from? Well, that's why this is a two-step process. So the first step, which you would not have to know, which you would not have to write the mechanism for, puts the OH and the mercury on there. Okay. All right. Is everybody with me? So let me rewrite that molecule then. So now I'm going to use a reagent that will replace the mercury with an H in exactly the same position that the mercury occupies. And that reagent is going to be sodium borohydride. So sodium borohydride has an Na plus and a BH4 minus. The BH4 minus is what I'm really interested in. So when you have a boron attached to hydrogen, the hydrogen is more electronegative than the boron, or you can say the boron is less electronegative than the hydrogen, which means that all the hydrogens have a delta minus charge and the boron has a delta positive charge. Because the boron is in like the metalloid semiconductor portion of the periodic table. So that basically means that sodium borohydride is the source of H minus, which is called hydride. And we'll talk more about hydride next semester. So basically that hydride molecule replaces the mercury in exactly the same position that the mercury was in. So that means that the final product will have an H where the mercury was, so that the net result is I've added H and OH across the double bond. The H ends up on the carbon with the most hydrogens, which makes it Markovnikov. And the H and the OH added 100% trans because of the triangular intermediate of the mercury ion. Okay. So this is a two-step process. Neither mechanism, I would ask you, or I would, ask you to write, but if you want to remember that mercury is like bromium, or is the bromonium ion, you remember it's a triangular intermediate. That helps you remember 100% trans. Okay. All right, so let's take this. Here's how the reaction would look. Step number 1, add mercury acetate and H2O. Step 2, sodium borohydride. So this is how you would see it in the book. This is how you're going to see it when I write it. So we don't have. So what we do is we just remember. Okay, what am I adding? So I've already got my CH3 on the top carbon. I'm adding an H-OH Markovnikov. That means the OH would go on the top carbon and the H on the bottom carbon. To set up the Markovnikov addition, then the OH and the H added 100% trans, so they have to go on opposite wedges like that. Now, all the rules about stereo and regio selectivity are still in play. So for this reaction, is it regio selective? If I added the OH to the bottom carbon and the H to the top carbon, would I get a different product? Yes. Did I select one over the other because the reaction's Markovnikov? Yes. So this is regio selective. Is it stereo selective? How many people say yes? It's stereo selective? How many say no? A lot of hands didn't go up. Okay. So I'm adding 100% trans. How many chiral centers in the product? There's 0 chiral centers. So how many do I need for it to be stereoselective? I need 2. I have 0. So this one's not stereoselective. Okay. So in the problems that were, I think, in the folder right after Thanksgiving, there were a bunch of reagents we didn't know. We now know one more. So it has all 4 of the cyclohexane combinations, or cyclohexenes plus the mercury, so that you can see when it's regio, when it's stereo. Remember, when it's stereo, you have to make 2 chiral centers in the product. And then it has to be 100% either cis or trans. So just a practical thing about mercuration, demercuration. It works for adding Markovnikov 100% trans. It's probably good for academic labs. It is not good for pharmaceutical synthesis. Mercury itself is a neurotoxin. And so having mercury in compounds is not recommended. For any of you that, if you've ever had to debate or look up the whole issue of mercury in vaccines, there was mercury placed in vaccines, a compound called thimerosal that was a preservative. It hasn't been in vaccines for probably over a decade. And so that preservative is, there are people that suggest, mostly Hollywood people with no medical degree, that might have been responsible for autism. You can look up the evidence on that by yourself. But because I'm not going to dip my toes into that controversial, which really isn't controversial. But there was actually mercury used as a preservative, and it's been removed. People used to play with mercury back in the 50s. You'd have mercury thermometers. We now know it's a pretty bad neurotoxin, so nobody's playing with mercury. There are no mercury thermometers, although I do have a couple in my lab. If they were to break, we would have to probably clear out the building.
What kind of problems? What kind of problems is it causing in the vaccine? Actual problems?
I don't know that they've ever shown clinically that it did cause. It was used as a preservative. People have claimed, though, that it's responsible for autism. They took it out. They found another preservative and they took it out. Yeah, that leads you to the whole thing of don't vaccinate your kids, which is probably not a very good public health position to take. But again, I'll let you discuss that with Dr. Lissamore or somebody else along the way. So we don't use mercury in pharmaceutical synthesis because the FDA would make you prove that every atom of mercury is out of your medicine, right? And we can detect low concentrations of metals, but I don't think we're at the atomic, like there's only one atom in there. I don't think we're that low yet. So, and mercury is a problem in fish. You can only eat so many fish out of Lake Erie because of the mercury that's found in them. In literature, if you want to go through the mirror with Alice, number one, if you go through the mirror, then all of your chiral molecules have become enantiomers. So hopefully they react the same way they do as their original enantiomers. Right, so you'd have a hard time finding stuff to eat that would be digested because all the sugars would be the wrong chirality. That's a question that actually a lot of people ask as an essay question in biochemistry. Like, what would Alice be able to eat and why? But the Mad Hatter, he wasn't angry. He had neurological diseases, including mental neurological diseases. Because in the old days, to make hats, they would take mercury to make the hats nice and stiff. So hatters were notoriously mad because they dealt with mercury. Without gloves, there were no gloves, and no fume hoods. So they were working with mercury a lot. So that's where that term comes from in literature. So a lot of the reactions when we talk about heavy metals, they work right on paper, but we would never use them in pharmaceutical synthesis. We have to find something else because we have to prove beyond the reasonable doubt that we've gotten every single atom of these metals out of there. So there's a lot, we've talked about chirality and stuff. There's a lot that goes into, even an aspirin or a leaf tablet. There's a lot of chemistry that goes into that. So anyway, this is mercuration, demercuration. Okay. Now, second reaction, I would like to add HBr anti-Markovnikov. I know if I just add HBr to a double bond, it adds Markovnikov. However, if I add HBr and a peroxide and H2O2 or HOOH, that's hydrogen peroxide. If we add organic groups to the end of the oxygens, we make an organic peroxide. So if we add the peroxide to HBr, we're going to get anti-Markovnikov addition, which means that the mechanism has completely changed to that of a free radical mechanism. Okay. Now, what is a radical? In chemistry, a radical is something that has an unpaired electron. That's a radical. So this is a carbon radical. This is an alkoxy radical. So number one, radicals are unstable.
Only has one electron, it's not a pair of electrons, right? It's just...
It has an unpaired electron. So it can never meet the octet rule, because until odds equal even, you'll never have an unpaired electron equaling 8. Okay? Because unless we change the rules of mathematics, that's not going to happen. So these radicals are unstable because they don't obey the octet rule. And I think in general, radicals are probably unstable, even in real life, some of them. So what happens is that if we have a radical, it's going to be an intermediate. Now, fortunately, carbon radicals behave almost like carbocation intermediates. If you think about the difference between a 7 carbon, or a carbon with 7 electrons and a carbon with 6 electrons, radicals are actually a little bit more stable than carbocations because they're closer to 8. So that means that every time you add an alkyl group, and how many times have we done this semester? I should ask, how many times have I done this semester? A lot. Where you add an alkyl group and we say, oh, the carbon is delta positive or delta negative, the hydrogen is delta positive. So the more alkyl groups, the more electron density we can push, the closer we can get the carbon to 8. It turns out that for radicals, a tertiary radical is more stable than a secondary radical, which is more stable than a primary. The difference between radicals and carbocations is I can legitimately draw a primary radical. Primary radicals exist. Whereas primary carbocations won't exist until next semester. And why? Because I'm starting with 7 electrons instead of 6. So I'm closer to 8. Okay. So that's something we have to keep in mind. That radicals act exactly like carbocations, and the other thing we'll see structurally is that the difference between a carbocation and a radical is it was an empty p orbital for the carbocation. It's now an orbital, p orbital with 1 electron for the radical. So we've now changed this mechanism to a free radical mechanism. And so here's how this mechanism works so that we're adding HBr anti-Markovnikov. Right. So in step 1, what happens is I take my peroxide and I break it apart. I cleave the OO bond. Now, since oxygens have the same electronegativity, there's an equal sharing there, and no one atom can take the pair of electrons away. So I'm going to split this evenly. And notice that I'm using the fish, these are called fish hooks. It's a half arrow, which means 1 electron. We've been using full arrows, which means 2 electrons for the semester. So this is a half arrow. So when I do that, I end up with 2 alkoxy radicals. Okay, so I make my alkoxy radical. Now my alkoxy radical reacts with an HBr molecule. And what radicals like to do is radicals like to abstract hydrogen atoms. That's what radicals do. And most of the time that's bad. But this radical is going to come in and it's going to abstract this hydrogen. So imagine my HBr bond breaking and then my O dot pairing up with the H dot so that I can now make my ROH bond. And then that leaves behind a bromine with an unpaired electron. Now you could say that's a bromine radical. Actually, it's just a bromine atom. So this radical comes in and it grabs the hydrogen atom, not the proton, the atom away from the HBr. And one of the difficulties with radicals is that once you form a radical, you basically don't get rid of the unpaired electron species until you run out of stuff. Because every time a radical reacts, it makes another compound with an unpaired electron. So then what happens? Then that Br dot decides that it's going to react with the carbon-carbon double bond. Okay. And what it's going to, if you can imagine taking the double bond and breaking it apart into the two unpaired electrons, I could either pair up the Br dot with the carbon on the left, which is going to leave me with a primary radical, or I could pair up the bromine with the carbon on the right, which is going to leave me a tertiary radical. So the bromine radical is going to add to the double bond. And what's different here is that I'm splitting the double bond to form basically having each of those two carbons have one electron. What do I pair the bromine up with? The carbon on the left or the carbon on the right? Well, which one of those two radicals is going to be more stable?
Carbon on the right.
Adding the bromine to the carbon on the right.
Yeah.
Because that makes a tertiary radical.
Yeah.
Okay? And so this is going to be that's going to be my major intermediate. So then what happens? Like all good radicals, that C dot wants to abstract the hydrogen, and so it abstracts a hydrogen from the HBr, another HBr molecule. And so the final product that I make now added HBr across the double bond, but it added the bromine to the carbon with the most hydrogens, and it added the hydrogen to the carbon with the least hydrogens, making that now anti-Markovnikov. So in order to do this reaction, in order to do HBr addition, anti-Markovnikov, I had to completely change the mechanism to a free radically based one. Okay. And notice that I started by breaking apart one peroxide molecule. In each of these steps, I kept making a species that had an unpaired electron. This is the problem with free radicals. Because once they react, they always generate another species that's got an unpaired electron, so it can then react. And so in our body, and we'll talk a little bit about this on Wednesday, we have to have mechanisms that stop this, right? Or else these free radicals, every time I breathe in, I'm taking in oxygen gas that has a certain percentage of it in a free radical form. And I don't have any alternative but not to take in oxygen gas. So those free radicals are running around grabbing hydrogens from things that I don't want them to grab hydrogens from. I don't want them to grab hydrogens from my DNA, or else I'll mutate into something, and maybe I'll get superpowers, maybe not. So we don't want radicals mutating stuff that it shouldn't be mutating. So we have antioxidant systems built in so that when that radical removes a hydrogen, the other species is really stable, and it kind of kills the process. But this is how that mechanism works, and it's our first sort of entry into free radicals. Okay.
I'm curious as to why the second component of the RO radical, why it wouldn't pair up with the tertiary radical that we created.
Because we have to realize there's a small amount of radicals in there. The likelihood that they're close together to pair up is going to be really small.
Okay.
Okay? All right, so we'll finish this up on